welcome to the very last session. So today we will be talking about decision trees, and more specifically, we are using the factors to build decision trees. As usual, let's just import those outside packages. Of course, also the AP module as well. And we also set the plotting style here. Then we just load the data. So when loading the data, we are loading the prices. That's just prices for the different stocks. We are using this .read CSV here. So .read CSV can actually not only directly reading CSV file, but can also read zip file that contains a CSV file inside. Then we build the future returns based on the prices data. So the future returns is just calculated as a form of a log return. So we have np.log on the very outside layer. And inside that log function, we are using the future period price, which is prices group by ID shift -1. So that's a future period price divided by the current period price, so directly prices. Then we also read the factor data. So that's the price data. We also have to load the factors data. So the first factor we load into Python is the profitability data. So that's gp.zip, that's gross profitability ratio. And then the second factor we load would be the momentum data. So that's a 12 months momentum. And we name that variable as MOM12. Then the third factor we load is the EP ratio. So that's the earnings divided by prices ratio. We name the variable as EP. Then finally, we have the volatility data. Actually, more technically speaking, that's a low volatility data. So instead of the beta values themselves, we are actually taking the negative values of those beta values, because we basically want the low volatility stocks to be ranked higher, to be ranked on the top. Now we are just, so here this cell is that we are just creating the features like X, and also we are creating the target, the outcome variable. So, or in other words, we are creating our labels. So we are creating Y here basically. So for X, it's very simple. So for X, when we are extracting X, we are just taking, oh, sorry guys, I skipped a step here. So what I forgot to mention is that after importing all the data, after importing the prices, and creating future returns based on the prices and loading the factors data, what we do next is that we are combining all things together. So we are combining the factors with the future returns. So here we create a new variable called as dB, and we let dB to be equal to the GPE, that's a gross profitability, joined by the momentum factor, and then joined by the EP ratio factor, and then joined by the low volatility factor, and then joined by our future returns calculated. And also we want to drop the NAs. So yes, let's execute that cell. Might take a while. Then let's just extract the futures and labels as we discussed earlier. So for X, it's really easy. So dB is basically our whole data set, right? So where we have both the features and also the future return. So we can see from the data structure here that our features are basically just the 4 columns before the last column. So we will be basically, when we are extracting the features, we will be just extracting those 4 columns. So X would just be equal to, so db.ilog, and this sign here represents every row. And for the columns, we are taking from the very beginning column to so -1 represents the last column. But remember that whenever we are doing slicing in Python, we stop at either one row or one column before. So here we are stopping at one column before the last column. So essentially we are starting here from GP, and we will be stopping when we are doing the slicing, we will be stopping at the beta column. So we are essentially just taking those 4 columns by using this ilog here. Now we are also creating the label, creating the outcome variable. So for the outcome variable, we are basically thinking that the return greater than the median return being a good return. So if it's not greater than greater than the median, then it's considered as a bad return. So we will be assigning the value of 1 to the good returns and the value of 0 to the bad returns. So that's basically what this line of code is doing here. So it's comparing the future return with the median of future return itself. So of course, the median of the date. So when you are on a specific date, you have lots of different assets, lots of different stocks. So you are actually taking the median of all those stocks on that specific date. So you can see that there's not any look ahead bias here because we are just taking the median of the returns on the same date. So here we are just basically comparing the future return with the median, and also we will let if the future return is greater than the median, then we will just basically view it as a good return and assign the value of 1. And otherwise we will assign the value of 0 to the y. Now let's also execute that cell. And then we are just doing the train test split. So for the train test split, here we basically want the data from 1990 to 2014 to be used for training. So that's our slicing here based on the index slice. Here, index slice is that we are basically doing the slicing based on the specified level of index. So here, when we use this PD.index slice, so this means that we are taking all the values of the first index. Remember, it's a stock ticker, that's the ID, right? And here for the second value here, like for those 2 dates, this basically means that for the second index, we are taking the index values between those 2 dates. So here, essentially using this PD.index size, that's sort of giving us the index we desired. So the index we desired is that we are keeping all the stock tickers and we are keeping the dates between those 2 specified dates. So that's basically the rows we wanted, right? So that's why we put it on the left-hand side here inside the log. So inside the LOC here, on the left-hand side, we are putting this index slicing. So that's basically the row numbers we wanted. And then this sign here, that sign represents that we want all the columns. So remember that X is already containing 4 features. So we are taking all the columns because we want to take all the 4 features. Now for the X test, the logic is the same. So the only thing different is that now we only want data from 2015 to 2019. So we're essentially just changing those 2 dates. The rest is the same as X train. Then for the Y train and Y test, we are pretty much doing the same thing. It's just that we are extracting data from Y instead of X. Now let's train our model. So before I train the decision tree model itself, let me just use this figure to do a bit of a quick introduction to the decision tree. Those squares you see here, I don't think that's squares, that's perhaps rectangles. So those rectangles here, are actually just called as nodes in a decision tree. So, but we have 3 different types of nodes in a decision tree. So this node at the very top, that's a so-called root node. So you can see that basically it has like nodes located below it, but it doesn't have any nodes located above it. So that's a root node. It's just like the root of a tree. And then you have those internal nodes. So for an internal node, basically it has node both on top of it and also locating below it. So you can see that it's connected both ways. So it's connected both on the top and also on the bottom of the node. And so that's an internal node. So here, this very node is a root node, and these 2 nodes and those 4 nodes, they are all internal nodes because they are connected both ways. And then finally, we also have leaf node. The nodes at the very last row, those are so-called leaf nodes. So they are only connected from above, and they don't have any further nodes connected below. So that's a quick introduction about 3 different types of nodes. And also the tree will be built based on one fundamental measure. And that measure is the so-called Gini impurity. So you guys already have the definition of that Gini impurity on your lecture slides. So you can refer to that for Gini impurity. So GINI. The Gini impurity is measuring how impure the data set is. And the ultimate goal is that we want to minimize the impurity by utilizing the decision tree algorithm here. For decision tree algorithm, it keeps dividing the total data set into smaller subsets. By doing that, it wishes to minimize the average impurity of all the subsets. So hopefully that makes sense. Now let's just import the tree and feed the tree. So we just from the sklearn import the tree. So that's actually the entire tree module. And then we are doing the instantiating. Remember how we are creating a certain instance from our predefined class, right? Or in other words, we're creating a certain object from our predefined class, our predefined template. So here we are specifying the max depths of the tree to be 3. So we are using the decision tree classifier, and we are letting the maximum depth of that decision tree to be 3. Let me expand about the depths here shorter after me finish the training here. So let me do the training first. So let's execute that cell. Let me just execute that again. So this is our trained decision tree classifier. Now, before I explain how to plot the tree here, let me first explain what's the depth hyperparameter here. So if you specify the max depth to be equal to 3, essentially you will just be having 3 layers at maximum after the root node. So also let me explain the intuition of decision tree further. So for the decision trees, the intuition, it's basically partitioning our original data set into different subsets. So for example, at this internal node, we actually, let's see, at this root node, we are actually trying to partition our total data set based on the EPQ feature, right? That's our EP ratio feature. And we are partitioning our total data set into two subsets. So on the left-hand side, it always means that's a yes to our condition specified. So our condition specified is the EP ratio smaller than or equal to 0.018. So if it's a yes, then we will moving on to partition that. So if that's a yes, we will create a first subset. And if it's a no, we will create a second subset. And then for the first subset, so that's represented by this internal node here. For the first subset, we are dividing it further based on another feature, and that feature is a 12 months momentum. And also for the second subset, which is represented by this node, this internal node here, we are actually doing the further division based on our EP ratio feature again. So decision tree is dividing the total data set into different subsets based on different features at each node. And of course, we have to select the best feature and the best value at each node. Then how do we make that selection? How do we decide that? At the root node here, we are using EPQ as a feature that we want to make the division on. And also, how do we decide that 0.018 is the best value to do that partition, to do that division? So the answer is that we are basically like remember our ultimate goal is to reduce Gini impurity, right? So essentially that's also our ultimate, so to achieve that ultimate goal, basically, so we're trying to minimize the Gini impurity, right? And at each node, we actually know the Gini impurity of the current data set, like either the full data set or the Gini impurity of the subset. So to achieve our ultimate goal of minimize average Gini impurity, what we do at each step is that basically we try to maximize the loss on the Gini impurity. That's a core intuition here. The whole reason here that we are selecting EPQ and also the value of 0.018 is because that's this feature and this value in together. When using them, when we move into the next two subsets, like and this subset here, we are maximizing the loss on the Gini impurity. That's how the decision tree works. So basically, decision tree will keep on dividing the data into different subsets until the Gini impurity stops to reduce. So when Gini impurity no longer reduces, basically our training will stop. But sometimes we want to avoid the model complexity. Let's finally explain why we have max steps specified here. So sometimes we want to avoid a too complicated model. So that's why we have to specify the maximum of depths here. So if we specify the maximum depths, so it will stop as long as, like this case, as long as it has 3 layers below this root node. Of course, if let's say, for example, if as this second layer here, our Gini impurity already stops to reduce, then our training will stop here. So we actually have only 2 layers underneath the root node. But if it's not the case, and usually it's not the case, if it's not the case, if the Gini impurity keeps reducing after the second layer, then basically our max steps equals to 3 will be effective, and our training will be stopped at this third layer here. So that's the whole reason why we are specifying max steps here. Now that's enough explanation of the intuition of the decision tree and also the max steps hyperparameter. Now let's just plot the tree. So let's just execute this cell here. So I was previously just expanding this figure, right? So this figure can be achieved via this plot tree function. So tree, the tree here, that's a tree module from scikit-learn. And the plot tree function is a function from the tree module. And then inside the function, first we input our trained classifier, which is CLF. And then we also set the font size of our figure. And we specify the feature names as the columns of our features. Let me show you guys what's X columns. So that's our feature name specified. So basically, we are telling Python the feature names using this hyperparameter. Let's try out what the field equals to false will do. So I know what's the proportion meaning here. For the proportion, it basically means that if you set it equal to be true, you basically want the at each node, it's specifying how many percentage from the original data set this node is representing. Here for the root node, it's representing 100% of the data from the original data set. And for this node here, it's representing 14.8% of the original data set. And if you go further along this branch here, basically you will be calling this thing on the left-hand side as a left branch, and the thing on the right-hand side here as a right branch. Let's go further along the left branch. So for the left branch, like this node here, you have 4.8% of the original data set in this node here. This figure here is plotted under the hyperparameter that field is setting to be equal to true. Now let's see what figure we will be having if we set field equal to false. And also we are saving this figure here using plot.savefig. Also, if you execute that figure, that decision tree.png will be appearing at the same folder as your notebook, because here I'm putting the decision tree notebook underneath this folder. So basically I will be looking for that saved figure in this folder as well. Now let me change that to be field equal to false. It appears that all of the nodes are actually gray. Now set that to be equal to true again. Now let's further rating the tree. When we are applying the decision trees to those factor data, essentially what I want you guys to achieve is that you will be able to identify the rules that separate good stocks and bad stocks. So not really good stocks and bad stocks, but what are the rules for the good returns and what are the rules for bad future returns? Of course, if you want to be loose with the terminologies, you can also say that what are the rules for the good stocks and what are the rules for the bad stocks. So here, let's try to interpret or rating the tree. So the entire thing here can be called as a left branch, and the entire thing here can be called as a right branch. And this thing here, so on the very left, you can say that it's a leftmost branch. So it's a leftmost branch we are going to analyze. Here, it looks like that this stock is actually a bad stock. When you're starting from the root node, when you actually just sort of doing random guesses, so a half chance of being a good stock and bad stock, your Gini impurity measure will be equal to 0.5. As we can see that when we do the training, the Gini impurity measure does reduce, right? So it reduces from 0.5 to this 0.485. Let's also try to explain about the value, and then I will explain the core meaning of this leftmost branch. And after doing that, you will be able to know how to decide what are the rules for the good stocks and what are the rules for the bad stock. So here, basically, the values here, those are the probability values of our different classes. So we only have two classes. Those are the probability of class 0 and class 1. The first value being the probability value of class 0, and the second value being the probability value of class 1. If this condition is true, so if the EP ratio is smaller than or equal to 0.018, then we just do the further judgment. So we just develop the rule further based on the momentum factor. So if the momentum factor is smaller than or equal to minus 0.877, so if that's true, we will be going along this way. Otherwise, we will be going to the other branch. So also you can notice that this internal node here associated with the momentum factor, we can see that there is now more than half of the class 0 and less than half of the class 1. So meaning that this internal node here is containing more bad stocks. And then if you go further along this leftmost branch, so as we said earlier, if the momentum factor is low enough, is negative enough, then we just go further along this leftmost branch. Then we will be reaching at this node here. That's based on the profitability. So now if not only the momentum is low enough, but also the profitability is low enough. So if it's smaller than or equal to minus 0.356, so if this condition is true, then we go further along the leftmost branch. Otherwise, we go into the other branch. So otherwise, we will be going into this second leaf node here. So basically this branch. So now let's focus on the leftmost branch again. So for the leftmost branch, now, so let me start from the root node again. So if our EP ratio is low enough, and also if our momentum factor is low enough, and also if our gross profitability is low enough, then we will be finally reaching at the final leaf node here. And the final leaf node is actually a subset that potentially contains the bad stocks, because so the reason that we interpret this leaf node as a subset for the bad stocks is that it has the 0.587 probability of being class 0, and which means that it's generating returns lower than the median with a probability of 0.587. And on the other hand, it has a 0.413 probability of being class 1. So that's why this final leaf node is more likely representing a bad stock. And I also already expanded into economic intuition behind this decision rule here. As I said earlier, because you are just picking the stock with the low EP ratio, meaning that its price is already relatively expensive. So it has a risk of being overvalued. And also you are picking the stocks with low momentum. So not only expensive, but also low momentum. And then you move further along the branch is that you are having low profitability as well. So no wonder that the end result is that this branch is representing a stock with bad returns or a bad stock. Hopefully that helps you guys interpreting or reading the tree. And then we also have to decide the feature importance. So naturally, we want to know that which of the feature is more important to our model, right? So which feature is more important for making the decision of our good and bad stocks? So here, luckily, we can just directly use CLF dot feature importances. Then it will be giving us the importance of our all 4 features. Let's also create a data frame. So you can see that the feature importances property of our classifier will be giving us a NumPy array without any feature names. To visualize that, we actually want to create a data frame with feature names. So we create a new variable called as features, and we use pd.dataframe. And inside we put the previous NumPy array, and we let the column names to be equal to feature importance. And we also set the index to be x.columns. So remember, x.columns are directly just those 4 feature names, right? Now let's create features. And by creating a data frame containing the feature importances, we can now plot the feature importances. So we can just directly use features.plot, and we let the kind to be equal to pi, because you'll notice that those 4 percentages are actually add to 1, right? So we can create a pie chart based on that feature importance data. So we specify the kind to be equal to pi, and also we specify the name of the y-axis to be feature importance. And we also set the fig size and font size. That's how we get this figure here.